Okay, thank you, Matthias, for that introduction. As mentioned, I'm Nathan Burrow. This is joint work with Chinping Zhang while we were both at Purdue, and of course, Matthias, who is now at EPFL. So this talk is going to be concerned with mitigating control flow hijacking. So at Blue Hat this year, Microsoft made the interesting disclosure that 70% of the bugs are still memory corruption vulnerabilities. And these bugs are interesting because the control and data planes are interleaved, as I sort of have a little illustration here where the gray cells are data and the green cells are the code pointers. So you can imagine that if you have a memory corruption in your data, it can overflow into a code pointer, which allows an adversary to redirect the control flow of your application. So what we would really like is a defense that allows us to at least logically separate the control and data planes as illustrated here. So when thinking about code pointers, which are the subject of attack for these control flow hijackings, they sort of come into two different varieties. First, there are forward edge pointers. These are function pointers or virtual calls in C++. There's a well-known defense for these called control flow integrity that works by statically calculating target sets to limit where these indirect calls can go in practice. So to see how this works, consider a function pointer that's being used to make an indirect function call, and without any defense, it can target every executable byte in the program. But when you apply CFI analysis, you restrict this to some limited set of functions within the program. This analysis runs into some trouble because there can be a wide gap between when a function pointer is written and when it is actually used for the call, which means you run into all sorts of the typical static analysis problems with alias analysis, etc., trying to connect the exact set of function pointer writes that might flow to a given indirect call site. The next class of code pointers are backwards edge, and in particular, these are return instructions. So a natural question is, does CFI analysis style analysis work on the backwards edge? And so, it's the same sort of setup. You have a return instruction, and where can it go to? And the answer is, of course, every call site in the function that might, call the function that you're returning from. And so the answer is really no, CFI style analysis does not work for the backwards edge. And the reason is that because you have to include every call site for the function, if you're doing static analysis in the target set, you end up with these huge target sets, potentially, especially for popular, say, library functions. And as control flow bending and control jujitsu have shown, the larger these target sets get, the more insecure they are in practice. And so we feel strongly that for backwards edges, these sets are too large to provide meaningful security in practice, and that doing security really requires integrity for return addresses. And so, yes, so sort of to sum up the state of control flow hijacking mitigation today, over the past 10 years, there have been 50+ papers on control flow hijacking, dating back to Abadi et al.'s seminal paper, which did include a call for a shadow stack. Unfortunately, subsequent research lost focus on this and only paid attention to the forward edge problem, which means that now that we are getting deployed versions of CFI by Microsoft and Google, they only cover the forward edge, and we have no equally strong protection for the backwards edges that is being deployed today. And so our solution to this is shadow stacks. This is a well-known research area, which is why we're writing an SoK on it and trying to promote awareness to get people to actually deploy shadow stacks in practice. Shadow stacks work by separating return addresses from the data plane, which allows us to provide integrity for the return addresses. And it turns out that these are performant and highly compatible in practice. And so the punchline here is that we need to deploy shadow stacks with control flow integrity to have a complete mitigation against control flow hijacking attacks. So to illustrate why we need shadow stacks, I'm going to go through a control flow hijacking attack in a little bit of detail here. Here we see the program stack with one stack frame. It has the return address and a stack canary. Stack canaries are the strongest currently deployed protection for return addresses that are designed to present smashing the stack for fun and profit style attacks that use a contiguous buffer overflow to directly overwrite the return address. So if you put the stack canary, which is a sort of magic value in the middle, you can then see if it's been overwritten, and if it's been directly overwritten, you can detect an attack. So also on the stack frame here, I've put in a pointer and an array. So as you might imagine, we're going to write to the array, and eventually our buffer overflow is going to happen, which allows the attacker to control the value of a pointer. If there is subsequently an attacker-controlled write through this pointer, the attacker can bypass the stack canary entirely and directly overwrite the return address, say changing it to a pointer to a ROP gadget or the beginning of a sled of such gadgets to perform their attack. So what is a shadow stack? A shadow stack is a way of, as I mentioned, separating the return addresses from the normal program stack. So here we can see the program stack, which has a collection of stack frames on it or call frames on it for the different functions, which include the return address and any information needed for local variables, etc. And on the shadow stack, what we're going to do is pull out the return information so that it is separate and not subject to these buffer overflows, etc. So to see how this defense works, we'll return to our previous example here, where we're midway through it. So the attacker has already overwritten the return address, but now instead of returning and using this attacker-controlled value, we instead compared the return address on the program stack to the shadow return address. And if they mismatch, we can detect an attack, and we can take any action we like in response to this. Typically, people just terminate the program, but you can imagine more sophisticated recovery policies. So the key advantages of shadow stacks are that you know at runtime what function you were called from, which means that we can move from the static style of CFI defenses that are trying to pre-compute target sets to a more dynamic defense that is focused on remembering the return addresses correctly. So there's no guessing or pre-calculation required here. Simply by separating the code and data planes for backwards edges, we end up with this very strong defense for return addresses. And in particular, it's fully precise, again, because of this dynamic nature of the information, where the call happens before the return, so you know where you're supposed to return to if you can only preserve that information in the program. So here, this is an SoK, so I'm going to briefly introduce the shadow stack design space before moving to our recommended shadow stack for deployment. So there are two main methods of mapping from the program stack to the shadow stack. Starting with, on the right side of the screen here, the indirect mapping. So here you are maintaining two stacks, which means that for every call instruction which pushes the return address to the program stack, you have to add instrumentation to also push the return address to the shadow stack. And similarly for returns, you're going to get two pops because you're maintaining two logical stacks. The advantage of this approach is that your shadow stack is very small. It only has to be as large as needed to store the return addresses and maybe the stack pointers to support recursion and so forth. The alternate scheme is direct mappings. So here you're only maintaining one logical stack. There's only the program stack that you're going to push to and pop from, but you're going to create a shadow stack that is as large as the program stack, which means there's a direct one-to-one mapping or correspondence or mirroring from the program stack to the shadow stack. So given any byte in the program stack, you do a little bit of arithmetic to say add a constant, and you directly arrive at the relevant shadow stack address, which means that once you push to the return address to the program stack, it's very natural to propagate it to the shadow stack without having to do this additional data structure maintenance. So this is sort of trying to do a performance versus memory trade-off where you're trading the extra memory of allocating the shadow stack that is as large as the program stack, but hoping to get better performance because the mapping is simpler. So our recommended shadow stack turns out to be an indirect mapping that uses a general purpose register to store the shadow stack pointer. And we find that this leads to optimal performance in terms of both processing time and memory use and high compatibility. And I'll now walk through why this turns out to be so. So for the mapping, the indirect mapping, to evaluate this, we took all existing techniques for shadow stacks and a couple more that we identified as missing during our survey. We implemented them all in LLVM7 and went and did some quantitative analysis and found that when using a general purpose register, the indirect mapping can be as performant as a direct mapping. And because it also saves memory space, obviously we go for this because it's a rare case of having our cake and eating it too, because the fastest mapping also has the lowest memory overhead. So as I mentioned, we're recommending using a general purpose register for the shadow stack pointer. There's been lots of discussion about, does this lead to increased register pressure? Is this going to be terrible for performance? And the answer turns out to be no, that on 64-bit architectures, which have 16 general purpose registers, all applications we evaluated, not only the SPEC CPU 2006 benchmarks, but also a wide variety of image processing and other desktop applications from Phoronix, as well as the Nginx web server. There was no huge performance hit from using a general purpose register, and in fact, it was the fastest scheme. So the takeaway here is that dedicating a register to the shadow stack pointer is actually an effective optimization across a very wide range of applications. So the last issue here is compatibility, which we evaluated along 3 dimensions. The first is support for threading. So of course, every thread in the program has its own stack, and you need to be able to support a shadow stack or program thread as well. Using a general purpose register to store the shadow stack pointer. This is very natural because general purpose registers are thread local, and so each thread has its own copy of this, which points to the relevant shadow stack for that thread, and everything works nicely. The next issue is stack unwinding, which is mainly used for C++ exception handling, although there are some other uses. The interesting thing here is that calls and returns are no longer a one-to-one correspondence. When you have a leaf function that throws an exception, you might unwind multiple stack frames and thus have multiple calls that don't have a matching return because we're directly going further up the stack until the exception is handled. So this turns out to be a non-trivial but not fundamentally interesting engineering challenge to deal with, and we provide an instrumented version of libunwind and setjump and longjump to handle this. Similarly, for unprotected code, there's this issue that when you cross the protection barrier, you have to save your shadow stack pointer. And again, we provide a solution for this. And so the punchline again is that we support all applications and incremental deployment. So we really believe that shadow stacks are mature enough to start being deployed with control flow integrity. So we've talked some about separating the code and data planes. And so there's this interesting question of, now that we have our return addresses in a separate location, what additional security can we provide for them? And in particular, because they're separated out, we can provide integrity protection. Return addresses have this nice property that they're only supposed to be written by call instructions, which means there's a very narrow window that we can identify what the correct writes are that should be allowed in our shadow stack. So to do integrity enforcement on the shadow stack, there are 3 techniques that we were able to identify. The first is a software-based randomization technique. Unfortunately, as shown by research on ASLR, these are defeasible in practice through information leaks and other techniques. So then we looked at 2 hardware-based schemes that we hoped would provide more sound protection at good performance overhead. This did not turn out to be the case. The first one we looked at was Intel's Memory Protection Extensions, or MPX. This provides hardware support for doing bounds checking. And so as shown in our previous paper, CFIX at NDSS 18, you can turn isolating a region of process memory into a bounds checking problem at moderate performance overhead. The newest scheme that we looked at here is Intel's Memory Protection Keys. This is a cool new hardware feature that allows you to assign virtual pages or ranges of virtual pages to one of 16 groups. They then provide an unprivileged hardware instruction to toggle the read-write permissions for all virtual pages in that group with a single instruction, as opposed to having to do a improtect call that does a page table walk and ends up with huge amounts of overhead. Unfortunately, when you use the MPK instructions across the call and return boundary, for whatever reason, you end up with terrible performance, something they've done microarchitecturally. So none of these are really fully satisfactory. We need new hardware solutions. This issue of doing intra-process memory isolation comes up not only for shadow stacks, but for any defense that wants to maintain some sort of dynamic state information about the application. For instance, the type safety defenses come to mind here. Personally, I'm a big fan of tagged architectures and believe that they will provide an interesting and performant way to do this in the future. So finally, I just want to sort of wrap up by highlighting some of our performance evaluation results. I'm running short on time, so I'll go a little bit quickly here. But the punchline here is that our recommended shadow stack has 3.65 overhead on average, and that this is lower than the direct shadow stack mapping, which was previously thought to be the most performant. And then here are the overheads for the different integrity enforcement mechanisms that we just talked about, where randomization adds about 1%, and then MPX comes in at 12% and MPK at 61%, but it has this huge outlier of 420% in some cases. So in conclusion, the stack remains vulnerable to code reuse attacks. The solution for this is to separate return addresses from the data plane, and to do so, we recommend using a compact register-based shadow stack. And really the key takeaway from this talk is that you need to combine shadow stacks with control flow integrity to have complete and practical control flow hijacking mitigation. Our code is available or will be available shortly at this URL on GitHub. And with that, I'm happy to take any questions. Thank you.
Awesome. To the second, 16 minutes. Any questions? Yes, please.
Nicholas Carlini, Google. Have you thought at all about the hardware shadow stack implementations like Intel has? I think it's CET and there are others. What are your thoughts on those?
Yeah, so CET will be great if and when they ever actually manufacture it. And
Sure.
Of course, it will only apply to x86. So there's this question of how do you protect ARM, what do you do for legacy processors, and so forth. So even with hardware support emerging, there's still going to be at least a rather large window where shadow stacks and software-based defenses are necessary.
Oh, thank you.
Hi, I'm Nir from Intel. That was exactly my question. So I'll ask another one. Can you comment on Harvard versus von Neumann as far as separation goes, if you're designing something new?
You said hardware diversity?
I'm sorry, Harvard versus von Neumann.
The two kinds of architectures.
Oh, Harvard and von Neumann. Excuse me, sorry. Yes. So I think from a security perspective, a Harvard architecture would have been better, although I understand historically there were excellent reasons at the time for doing the von Neumann approach of mixing code and data, which is why I think we're sort of at the point now where what we really need is a logical, if not necessarily a physical separation of the two.
Thank you.
Hey, Manuel Egele, Boston University. This was very amazing. I like this stuff a lot. I had one question. You said you implemented the various schemes that you found in LLVM 7. So what did you do with the libraries that were linked into those binaries? Did you also recompile all of those?
So when we were evaluating things, we recompiled libc. For some of the others that had dependencies, we did not. We looked at recompiling all of FreeBSD for full support and just weren't quite able to make it work in time for the deadline.
Any other questions? Okay, let's thank Nathan again.